Stop worrying about homework and start learning with confidence. This is Ask Learn. Complete help for every subject. Like, share, subscribe for daily learning videos.
Hello. In this problem, we're asked to figure out what the net torque is going to be on a rectangular loop that's in a current carrying rectangular loop that's in an external magnetic field. And we're also asked to basically determine which way this loop is going to rotate, because we know it's going to be experiencing a net torque. So which way is it going to rotate? Is it going to rotate such that that 35-degree angle increases as time goes on, or is it going to rotate such that it decreases as time goes on? Now, to figure out the first part, it's actually a little easier when we view the image we have in the book from the top. So let's draw that out right now. So if we view it from the top, let's say that our x direction is actually headed downward. Our y direction is headed to the right, and that means our z direction will be heading out of the page. Now in this case, that means our current carrying loop is off at an angle, right, of 35 degrees. Here, let me draw those a little bit better here. We have our loop, current carrying loop, out at an angle of 35 degrees. And we also know that our magnetic field is directed completely along this y direction. Okay, that's important because when it comes to figuring out the first part, A, determine the net torque exerted on the loop, well then we have to know the parts of our equation that were given for the net torque on a current carrying loop, right? If we know the number of turns, the current through the loop, the surface cross-sectional area of our loop, and the magnetic field value, then we know part of the torque, but we also need to know the orientation, right? What is the angle phi that the normal to our surface area makes with the direction of our magnetic field? So we know most everything in this problem. We know the amount of turns, we know the current in the loop, we know the cross-sectional area because we know the length and width of this rectangle, so we multiply them together, and we know the magnitude of the magnetic field, but we don't know exactly explicitly the orientation, and that's why I've drawn it from a top down. So if we think about which way the currents are flowing in this diagram, we know that on the part of the coil that is along the z-axis, the current is heading out of the page. Now, not put the vector there for now. The current's heading out, and then on this side that's inside the first quadrant of the coordinate system, the current is going to be heading into the page here. So when we have a current heading out like this and into the page like this, we can use one of our right-hand rules to have our fingers follow the flow of the current, and then our thumb, like a thumbs up, points in the direction of the normal that we're going to consider. So since we have our current flowing up, and on the left side of this coil and the current flowing down on the right side, when we rotate our finger and have our thumb point out, the normal ends up being like this. And I'm exaggerating it to help us figure out this angle phi here. So this is going to be the normal, or the area vector, for our loop. Now, we'll see here that when we do this, we can figure out the angle between the area and the area vector and the magnetic field vector, because that angle is this one right here. This is the angle phi we want to find. Now, if we can compare angles between this angle here and this here, we actually see that they're the same. So this ends up being 35 degrees, and that means the phi we need for our equation ends up being 90 minus 35 degrees, because it has to make up that difference for the right angle, right? So if that's the case, then that means that this angle is 55 degrees. That's the angle between our area vector, our normal, to our loop, and the direction of the magnetic field. So now that we know that, we know everything we need to figure out the torque that's acting on this current carrying loop. So tau is going to be equal to the 75 turns that we have in this coil, multiplied by the current through it, which is 4.4 amps, multiplied by the surface area, cross-sectional area of this. I'm just going to move this down here, multiplied by the cross-sectional area, which is going to be the length times the width. So 0.7 meters multiplied by the width, 0.5 meters. That's the area. Then we're going to also multiply that by the magnitude of the magnetic field, the 1.8 teslas. And then we have to multiply that by sine of the angle we just found, which is 55 degrees. Putting all that into our calculator, we get that the answer is about 170 Newton meters of torque that this coil is experiencing at this moment. Now the question then is, for part B, is the 35-degree angle increasing or decreasing? Now remember, from the textbook, we know that if we can determine the direction of the normal, then coils are going to rotate such that the direction of the normal aligns with the external magnetic field. Well, if that were to be the case, let me draw a little purple coil here, right? If we want that to be the case, we want the normal to be aligned with the magnetic field, that means that the coil must rotate to orient itself like this, where our current is still heading out of the page on this side and into the page on this side. So what that means is that this coil is going to kind of swing out such that it's going to start aligning along the x-axis. So that means that this 35-degree angle then is going to be increasing such that, oops, write that better. It's going to be increasing so that the normal to this loop aligns with the external magnetic field. And those are our answers.